Welcome everyone. Let's discuss another question from GATE 2024 Life Sciences. The question is, the pK of a buffer solution with pH of 5 consisting of 0.4 molar sodium acetate and 0.04 molar acetic acid, and we need to report the value. What all information is given here? The concentration of acetic acid given, which is 0.04 molar. The concentration of sodium acetate is given, which is 0.4 molar. The pH is given 5, and we need to calculate the pK of this buffer solution. As you might be aware, buffer solution resists change in pH when an acid or alkali is added. Now, what we can do to calculate the pK, we can put these values into the famous Henderson-Hasselbalch equation, which is pH equal to pK plus log base by acid. Here we can consider acetate as a base, as it is formed by the ionization of a weak acid, which is acetic acid. So the acetic acid is carrying a proton while the acetate is not carrying a proton. So base we can consider acetate, acid we can consider acetic acid. But before that, one should know how to derive this equation. There is no need to memorize. It's a simple equation and we'll see how to derive it. So let's have a look. What I have written here is the ionization of the weak acid at equilibrium. Now this is the acetic acid. It's a weak acid and we'll see why. And this is its conjugate base, which is acetate. Now in the aqueous solution, acetic acid will lose its proton to give the conjugate base CH3COO minus, and we can write the acid dissociation constant for this reaction as concentration of CH3COO minus multiplied by H3O plus. Remember, when it will lose its proton, that proton will combine with the water molecule to give you the hydronium ion, and that's the reason I have written the hydronium ion at the product side, and K we can derive, we can calculate by multiplying the concentration of the products divided by concentration of the reactant. Why I have not considered water in the denominator? Because water is a pure liquid and it has a very high concentration, which is relatively constant throughout the course of the reaction. Now I can rearrange this equation, K into concentration of CH3COH, and in the denominator I can place acetate ion equal to hydronium ion. I can take negative log on both the. I'm just rearranging this equation so that I can come up with Henderson-Hasselbalch equation. Now, when I'll take the negative log on both the sides, I can write it in this way. Now remember, negative log of hydronium ion concentration is pH, and this I can rewrite it as minus log multiplied by this value, which will give me minus log Ka. Since this is in a multiplication form, I can write it as a plus. So minus log K plus minus log CH3COH divided by concentration of CH3CO minus. As you might be aware, log A into B, you can write it as log A plus log B. That's what I have done. Since it's a negative log, the sign is going to be negative. I hope you all are aware with such kind of a convergence, and I have used such kind of a convergence in rearranging this equation. So going back, you can rewrite in this way, and then we all know negative log of acid dissociation constant is the pK, and then you have the negative log of concentration of acetic acid divided by concentration of acetate ion equal to pH. I can rearrange this equation so that I can put a positive sign here, and to do so, I can rewrite it as pH equal to pK plus log. When I'm changing the sign, I can flip this. So I have written plus log CH3COO minus by CH3COH. Now this is nothing but a Henderson-Hasselbalch equation. And that's what I have written here. As said, base is the acetate and the acid is the acetic acid. I just need to put the value. pH given is 5 pH equal to pK, I need to calculate log concentration of base. The concentration of base is 0.4 molar and the concentration of acid is 0.04 molar. So I can rewrite those values. This is going to be pKa plus log. So this value is going to be log 10. So now we can calculate the pK. 5 equal to pKa plus log, the value of log 10 is 1. So pKa is going to be 5 minus 1, which is going to be 4. As I said, pKa is given by negative log of Ka, and K is acid dissociation constant. The stronger the acid, the higher the value of K is going to be. However, the relationship between the pK and Ka is inversely proportional because there is a negative log sign here. And so if a acid is strong, the Ka value is going to be high, but the pK is going to be low. And just to give you some number, the pK of strong acid like HCl is close to -6 to -7. Now have a look at the value of this pK. It is in positive and the value is 4. Much higher pK value. That means much lower Ka value. And this gives us the idea that the acid which is mentioned here is a weak acid. So writing the final answer, the pK of the buffer solution in this case is going to be 4. The other concept here is when the pH is close to the pK value, the buffer has a highest buffering capacity. So when the pH is equal to ±1 pK, the buffer has a highest buffering capacity. That means the buffer solution can resist the change in pH when an acid or alkali is added. I hope this concept is clear to each and every one of you. If you do have any query, feel free to comment. Thanks for watching the video.